Okay, today I want us to look at Bessel's equation. Now, Bessel's equation, as seen, it is a type of differential equation. It's a type of differential equation like the ones we had seen before, except that this one is a bit different from those ones. Like we said, we had like the Lagrange differential equations, the Legendre differential equations, and then we had the Hermite, we had the Chebyshev. Now, for those differential equations, their solutions were polynomials of degree n. But here, when you talk about the Bessel's differential equation, for it, its solutions are functions of order n, and they are series functions, which form series. That's why it is coming up at this point here, because it is under this topic we are looking at series solutions of differential equations. So Bessel's differential equation takes that form. It takes this form here in 1.4.1, and we want to see how we can get the solution, the series solution to this differential equation. This is going to be done. So we are required here to determine the series solution to Bessel's equation by the Frobenius method. Now, the Frobenius method, we had seen it before. It is the one we have been using actually. It is so not so as different, except that before we are talking about getting the series solution about a regular singular point, and we are saying that is when we use this expression. Otherwise, if the point is not a regular one, then we use just ak x power k. So the Frobenius method also assumes that we are getting the solution to this Bessel's equation at a regular singular point, but this time you can identify it clearly here that when x is equal to 0, then it's like the Frobenius method here we are applying is we are going to get the series solution to this Bessel's equation at the regular singular point x is equal to 0. And if that is what we are taking into consideration, then we begin by saying here that we assume a solution y equal to the sum from k is equal to 0 to infinity of ak x power m plus k. And then, as we've been doing before, we get the first derivative of this first assumption and the second derivative of that assumption, and then we substitute them back into the Bessel's differential equation, and by that we come up with this substitution here. Now, with this substitution here, having x squared outside here means we can pick it and put it inside the summation, and it reduces this power to m plus k, and then this x put inside reduces the power at this point to m plus k. X squared increases the power at m plus k plus 2, and this is 1.42 is the output. It's the output after we substitute the derivatives. Now, next we are supposed to alter the powers to m plus k, but here there is only this sum which has that m plus k plus 2. And if we say that now we want to alter the powers, it means it is this sum which we have to put our attention to alter this power of m plus k plus 2 to be m plus k. And to do that, we begin by saying that let m plus k plus 2 be equal to m plus k, and that would mean if we make this m plus k the subject, it should be equal to m plus k minus 2. And then we get that m plus k minus 2, push it at this point, and it would leave here for us m plus k, because I have m plus k minus 2 plus 2. So that will leave us with this point with m plus k as the power. Now the way you are altering this sum is not so different from the way you have been altering up there. It means you can alter this area here according to your convenience of understanding on how the powers can be altered in any given sum. But then we know that after altering the power, even the coefficient of k, the subscript k here, should be altered using the transformation m plus k plus 2 is equal to m plus k. So that means that the k on the left hand side would be equated to m plus k minus m minus 2, and then the minus m will cancel this m, and the minus 2 will remain here at k minus 2. So you find here that the subscript for k in this sum that we are altering is going to be reduced to k minus 2. I'm not using the explanations that are appearing there. I'm not using the explanations that are appearing here because of the fact that we have used different ways of doing the alteration up there, so I don't want to confuse you. But the explanation I'm giving you up here can still tell you how this subscript k is going to reduce to k minus 2 in 1.44. So from 1.42, after altering the power here to m plus k, we are landing here at 1.44. And after altering those powers, the next point should be, since now the power of x is the same for all the summations, it means then we get the coefficients of each sum and we add them and we equate the coefficient to 0. And so that gives us this step here. You get this coefficient plus this coefficient plus ak minus 2 plus n squared ak is equal to 0. Then we get what we call a recurrence relation that is going to help us generate the coefficients, the ak coefficients in our series solution. So in this recurrence relation, yeah, it is just organizing this equation, and you make ak the subject, which will give you this as the output component. Now in this recurrence relation, we need to know to have an initial equation that is going to be used for our series solutions at the bottom there. So we say that at k equals 0, put into this recurrence relation, that will give us a minus 2 in the numerator into m squared minus n squared, and so that will give us m squared minus n squared. If you cross it on the left hand side here, to give us n naught into m squared minus n squared as equal to negative, the numerator here, a minus 2. But when we look here, a minus 2, we have to know here that the summations in this equation 1.4, they are all originating, like for y, it originates at k equals 0. Then for the first derivative substitution, it originates at k equals 1. And for the second derivative substitution, the sums begin at k equals 2. So that would mean here that at a minus 2, we can't attain it in what we are doing. And the coefficient at a minus 2 cannot be attained because we begin from 0 at k is equal to 0, k is equal to 1, k is equal to 2 for the second derivative. So this automatically means that this coefficient should be equal to 0, implying here that we are fetching a product of 0 between m squared minus n squared into n naught as equal to 0. Implies then that either n naught is 0 or this one is 0, but we say that n naught cannot be equal to 0, implying that m squared minus n squared should be equal to 0. So if m squared minus n squared is equal to 0, at k equals 0, it gives us m as plus or minus n as the solutions to the initial equation. So those solutions to the initial equations, we said the other time, they are used to fetch the solution, the y1 at x solution and the y2 at x solution for the different substitutions of the m at plus n and m at minus n. So begin for the first case for m is equal to n, and we substitute that m is equal to n into the recurrence relation that we got. So the recurrence relation is here. At m is equal to n, we put n here plus k squared minus n squared, and when you simplify, then you are going to get this as the output recurrence relation when m is equal to n. So we use this recurrence relation to generate the coefficients for the solution at m is equal to n, beginning at k equals 1. So at k equals 1, we have here 1 minus 2, which is a at negative 1 over 1 into 2n plus 1. Now a at subscript negative 1, it is the same story in our summations. It does not appear there, implying that a at subscript minus 1 is an automatic 0. And if it is a 0, it means then that at k equals 1, a1 is equal to 0. So our a1 is equal to 0. Then you go for k equals 2. So at k equals 2, we put 2 here, and then 2 minus 2, we get a0 over 2, 2n plus 2, and then I leave denominator at negative a0 for a2. And then for a3, we have negative a1. Let's see where we are substituting. So a3 at k equals 3. So we have 3. K is equal to 3 would give us a1 at 3, 2n plus 3. And then a1 is 0. That means a3 is 0. And k is equal to 4 would give us this. And the k is equal to 5 is 0. So we see here that when k is odd, the output a is a 0. So the coefficients that will be carrying value will be the even subscripts of a at a2, at a4, at a6, a8, and so on. And then these coefficients are fetching a sequence